Hello everyone. In this video we are going to talk about the calculation process of lateral earth pressure on retaining structures by using Rankine theory. So here we have a big problem. We have a retaining wall. The depth of excavation is 5 meters and the groundwater table is not at the same elevation on both sides of the retaining wall. Here it's 2 meters below the ground level, and on the left hand side it's on the ground level. So in this problem we want to draw the active earth pressure and the passive earth pressure distribution on the retaining wall, and we want to calculate the resultant force on this retaining wall as well as the point of location. So here at the very beginning you must have enough knowledge to know that this retaining wall in these conditions will rotate anti-clockwise around its base after the excavation process. So when it rotates anti-clockwise, as can be seen on your screen right now, you will find that the soil on the right hand side will exert active earth pressure on the wall because the wall is moving away from the soil. However, on the left hand side of the retaining wall, the soil here is being compacted by the wall because the wall is moving towards the soil. So here you have a passive condition, and the soil on the left hand side exerts a passive earth pressure on the retaining wall, so we have here a passive condition. So we have to calculate K active and K passive for the different soil layers in our problem. We have for the uppermost 2 meters we have a clay soil with C of 20 kilopascal and gamma unit weight 18 kilonewton per meter cube. Then we have a sand layer with an internal friction angle of 30 degrees and unit weight of 16.5 kilonewton per meter cube. Then we have maybe silty sand layer which has a cohesion of 20 kilonewton per meter square. It may be clayey sand and a phi value of 30 degrees and unit weight of 18 kilonewton per meter cube. So for the 3 soil layers we have to calculate K active and K passive. K active it's 1 minus sine phi over 1 plus sine phi. So for soil number 1, this is soil number 1, you only have to calculate K active. So it's 1 minus sine phi. Phi is equal to 0 for soil number 1. It's a clay soil. So 1 minus sine 0 over 1 plus sine 0, it's equal to 1. So K active for the first layer, for the first clay layer, it's equal to 1. For the second soil, which has an internal friction angle of 30 degrees, it's a sand layer, K active will be third, 1 minus sine 30 over 1 plus sine 30. And for the K passive value for the second layer, actually the second layer has the same K active as the third layer. The second and the third layer, both of them have a K active value of third because both of them have an internal friction angle of 30 degrees. So for soil number 2 and for soil number 3, they have the same K active value, which is third. However, on the left hand side they have a K passive value of 3 because we already know that K passive it's equal to 1 over K active, so the K passive for both of them is equal to 3. So now let's begin the process of calculation of lateral earth pressure. First of all, we have to determine the locations at which we will compute the pressures. So first of all, on the right hand side of the retaining wall, which we will use the active earth pressure equation, let's begin looking at the points at which we will compute the lateral earth pressure. First, the uppermost point of your retaining wall here, this is point number 1. Then, moving downwards, you will find here at this location that you have the groundwater table. But you also have at this elevation a difference between two soil layers. So this elevation actually, it's between two different soil layers. The upper soil layer has a gamma of 18, the bottom soil layer has a value of 16.5. The upper soil layer has a C value, however the bottom soil layer doesn't have a C value, it has only an internal friction angle. So at this elevation, as we have said in the last two videos, you have to determine the pressure at 2 points. One point is just above this elevation and the second point is just below this elevation, so you have 2 points at the same depths, which are 2 and 3. The point number 2, it's controlled by the properties and the parameters of the upper soil layer. However, point number 3 is controlled by the parameters and the properties of the bottom layer. Then, moving downwards, you have another elevation which marks the difference between two different soil layers. This elevation is between two different soil layers. So here you must calculate your pressure 2 times, one just above the elevation and the second point will be just below the elevation, so you have here 2 points, 405. Point number 4 will be more controlled by the above soil layer, which is soil number 2, which has an internal friction angle of 30 degrees. However, point number 5 will be controlled by the soil layer, which has C of 20 kilopascal and phi of 30 degrees. And at the very end, you have point number 6, which is at the base of your retaining wall. On the left-hand side of your retaining wall, which will be calculated using the passive earth pressure equation, you have a point here, which is point number 7. It's at the base of your excavation. Then you have here an elevation which is between two different soil layers. So you have 2 points here, one above and one below, 0.8 and 0.9. And at the very end, you have at the base of the retaining wall point number 10. So here in this problem, we have 10 points. So we will do the calculations 10 times. 6 points from 1 to 6, you will use the active earth pressure equation. And for 4 points from 7 to 10, you will use the passive earth pressure equation. So here in this slide, we will do the calculations of the active earth pressure for the points from 1 to 6. So at point number 1, don't just say that I am at the ground surface, so the earth pressure is equal to 0. That's wrong. At point number 1, you have to stick to this equation. Just substitute in this equation. Yes, since you are at the ground surface, the value of gamma h is equal to 0. It's 18 by 0. You are at the ground surface. But you have a life load value here. You have a life load of 20 kilonewton per meter square. K active is equal to 1 because you are in the clay layer, the uppermost soil layer, and you have a C value here. So it's minus 2 by C, which is 20, by square root of K active, which is 1. So here you have an active earth pressure of negative 20 kilonewton per meter square. And actually, yes, it's very normal to have a negative value of active earth pressure if you have a clay layer. If you have a clay layer, this term in the equation will not be equal to 0. It will be a positive value. 2C by square root of K active will be a positive value. So if you subtract this value from the first term of the equation, most probably you will have an active earth pressure value, a negative value. So it's very normal, especially if you have a clay layer which is stiff or very stiff, or even soft clay with low values of surcharge. So if you have a very big value of C and a low value of life load, so the first term is small and the second term of the equation is big, so you will have a negative value for the active earth pressure at the uppermost point on your retaining wall. For second point, you have to calculate the own weight of the soil, effective vertical stresses at this elevation, which will be 2 meter by gamma, which is 18. Then you have 18 by 2 plus life load 20 by K active 1 minus 2 by C. C is equal to 20 by square root of 1. This will be 16 kilonewton per meter square. Then at point number 3, remember that you are at the same depths. So remember that at point number 3, you have the same life load and you have the same effective vertical stress on this point at this depth. So at point number 3, this term which is representative of the effective vertical stress and the life load, it's the same here because you are at the same depth. You have the same vertical stress above and you have the same life load, so it's the same term. What changes from E2 to E3 is the parameters of the rest of the equation. The value of K active will be different and maybe the value of C will be different. So point number 3 gets its parameters from the middle soil layer, which doesn't have a C value and has a K active of third. So it will have a K active of third, and the second term of the equation, 2C by square root of K active, will be equal to 0 because C is equal to 0. So E3 will be 18.7 kilonewton per meter square. For E4, you have to calculate the effective vertical stress or the own weight of the soil from the ground surface to the depth of the point 4. So as long as you are above the groundwater table, use gamma saturated of the soil, and if you are below the groundwater level, use gamma submerged. So at point number 4, the effective vertical stress will be 18 by 2 gamma saturated by 2 meter plus gamma submerged, which will be 16.5 minus 10, so it's 6.5, then 6.5 by this height which is 3 plus 1.5, 4.5. So the effective vertical stress 18 by 2 plus 6.5 by 4.5 plus your life load. Don't forget about your life load, which is 20. Then the parameters of the rest of your equation, just look at your point number 4. It lies within soil number 2, the middle soil layer, which doesn't have a C value and have a K active of 1/3. So I substitute here with a K active value of third. Then E4 it's equal to 28.4 kilopascal. 0.5, remember that 0.5 is at the same depth as 0.4, so it has the same effective vertical stress as 0.4. So this bracket, this term, it's the same here because you are at the same depth. You have the same effective vertical stress and you have the same life load. However, take care, keep in mind that point number 5 in a new is in a new soil layer. It takes its parameters from the bottom layer, which has a C of 20 and 530, so K active is equal to third. So K active is third, but we have a C value here, so we have to subtract this term, minus 2 by 20 by square root of third. This is 5.3 kilonewton per meter square. The last point, which is point number 6, we have to calculate the effective vertical stress and the life load. It's an easy point, and I will leave it. It will be left for you to try it at home. For the passive earth pressure calculations, we have 4 points, which begin from point number 7 up to point number 10. The equation, according to Rankine theory, it's gamma h by k passive plus 2c by square root of k passive. Here on the left hand side of the retaining wall, we don't have life load, we don't have a surcharge. So in the equation, I don't write here life load. I omitted this term because I don't have a life load or a surcharge on the left hand side of the problem. So for point number 7, don't just say that it's equal to 0 because you are at the ground surface. It can be, or it can have a value if you have a cohesion in the middle soil layer. So just stick to the equation, just substitute in this equation, and you can then see if you will have a value of 0 or not. So at point number 7, you don't have a cohesion in the middle soil layer at which the point number 7 is existing, so this term is equal to 0, the second term of the equation, and the first term of the equation, it's gamma h by k passive. You are at the ground level, the h is equal to 0, so E7 is equal to 0, but it's not always the case. E7 may be equal to a certain value if you have a cohesion in the middle layer, or if you have a surcharge or a life load on the left hand side of your retaining wall. For E8, you have here, you want to calculate the vertical effective stresses at point 8, which will be the gamma submerged, which is 6.5 by the height 1.5. So 6.5 by 1.5 by k passive, which is equal to 3. Point 8 lies within the middle soil layer, which doesn't have a C value, so the second term is equal to 0. For E9, E9 has the same effective vertical stress as E8. So this term will be used here as it is. By K passive, for point 9, take the parameters and the properties of the bottom layer. It has a K passive of 3, but it has a C value. So here I will add plus 2 by 20 by square root of 3, which is a K passive. So E9 is equal to 98.5 kilonewton per meter square. For point number 10, it will be left for you to try it at home. Don't forget the water pressure on both sides of your retaining wall. You have a triangular water pressure. On the right hand side, this depth from the groundwater level to the base of your retaining wall is 6 meters. So you will have a triangle starting from 0 at the groundwater level and increasing linearly to 60 kilonewton per meter square at the base. On the left hand side, you have the groundwater table here, and the distance between the groundwater table and the base of the retaining wall is equal to 0. This distance or this height is 3 meters. So the pressure will be 10 by 3, gamma water by H water is 30. So you have here a triangle. You have here a triangle which will start with a 0 value at the groundwater level and increasing linearly to 30 kilopascal at the base of the retaining wall. So this slide summarizes the calculations we made in the last slides. You have 6 points on the right hand side which were calculated by the active earth pressure equation. Just you have to plot these values and draw your diagram. So if you have here, this is your datum, a vertical line, this is your datum, a vertical line. You have E1 of negative 20. So you plot your value on the left hand side of the datum. Then it increases linearly from negative 20 to 16, which is E2. Then E3 at the same depth, there is a sudden rise, a sudden increase in pressure from 16 to 18.7, which is E3. Then E4, it's 28.4. So there is a linear increase from 18.7 to 28.4. Then at the same depth at E5, there is a sudden drop from 28.4 to 5.3. Then there is a linear increase from 5.3 to 9.3. On the left hand side of your problem, you have 4 points from E7 to E10, and E7 is equal to 0. Then there is a linear increase to 29.3. Then a sudden increase at the same depth from 29.3 to 98.5 and increasing linearly to E10, which is 134.5. And at the end, don't forget to draw the water pressure on both sides of your retaining wall. You have on the right hand side a water pressure starting from 0 to 60 kilopascal, and on the left hand side a triangular water pressure starting from 0 and ending with 30 kilopascal at the base of your retaining wall. A very important comment you have to consider in your problem here, that we have here a zone of negative earth pressure, negative active earth pressure. We said that we normally have a negative value of active earth pressure at the very top near the ground level if you have a clay layer. In this case, this depth, the depth at which we have negative values of active earth pressure, is corresponding to a tension crack. We have in this depth what's called or what's denoted by a tension crack. These tension cracks take place in clay layers near to the ground level. Actually, this means that this depth at which we have negative active earth pressure, if you convert these negative stresses into forces, you will have a force in this direction, from the left hand side to the right hand side, you will have a resisting force. You will have a resisting force. So practically, we don't depend on these resisting forces, we just neglect it. We neglect the existence of these forces. We don't depend on these resisting forces at all in our design. We neglect it. Yes, theoretically, you may have a tension crack, you may have a 1 meter or 2 meter below the ground level in which the forces are resisting the failure of the retaining wall. They are pushing the retaining wall again towards the soil and they help in the resistance. However, in practical design, we don't depend on this resisting forces and we neglect this zone. So at the very end, when you are computing the resultant force on your retaining wall, and while you are computing your overturning moment or the resultant moment around the base of your retaining wall, you have to simplify your geometry and simplify or divide your diagrams into familiar shapes, which are triangles and rectangles. So this zone, as we have just said, will be neglected, and starting from this triangle you will deal with the problem. So the area of this triangle will be the first force F1. The area of this rectangle will be F2. The area of this triangle will be F3. The area of this small triangle will be F4. Then the area of this small triangle will be F5. The area of the triangular water pressure will be F6. Of course, at any time if you have a rectangle, you of course know that the force will act at the centroid, so the arm, you can determine the arm very easily. And for any triangle, you must know that the force will act at the centroid, which is at the third of the height of the triangle. On the left hand side, you have this small triangle. Its area is F7. You have this rectangle. Its area is F8. And this small triangle, its area is F9. And this small triangle, its area is F10. So you have 10 forces. And you will compute all of them by just calculating the area of the corresponding rectangle or the corresponding triangle. And you can, of course, calculate the arm of each force of them away from the base of the retaining wall. Just we have a small problem we have to deal with right now, that for the force F1, if you want to calculate F1, it's equal to the area of the triangle, which will be half by base by height. The base of this small triangle is 16. However, we don't know this height. So if you want to calculate this height, you will take this part of the problem, these two triangles here. You have the upper triangle, the ordinate here is 20 kilopascal, and the ordinate of the smaller triangle here is 16 kilopascal. So the upper triangle is 20, the lower triangle is 16. So we can use an equation, 16 over 20. We can assume that this distance, the height of the smaller triangle, is x. So the height of the other triangle is 2 minus x. So in this case, 16 over 20 is equal to x over 2 minus x. So using this equation, we can solve this equation by using our calculator, and we can get x, it's equal to 0.89. So now you have the height of your triangle, which is 0.89. So it's half by 16 by 0.89. Now you can get the value of F1 for every meter run of your retaining wall. And of course, the arm of this force from the base here of the retaining wall, you have this distance is equal to 3 meter, 1.5 plus 1.5 plus 3 meter plus 1/3 of the height of the small triangle. So your arm will be 3 meter plus 3 meter plus 1/3 of your triangular height. Triangle height is 0.89. This is the arm of F1. Using the same approach, you can calculate the values of F2 to F10 and the arms. I will leave the calculations on the slide. You can calculate the values of F2 and F10 and use the calculated values on your screen right now as a guide. So after the calculation of the forces from F1 to F10 and the calculation of the arm, you can calculate the moments. But there is a very important note you have to consider here. When calculating your forces, you must assume a direction for the positive sign and a direction for the negative sign. We will assume here that any force moving to the left will take a positive sign and any force to the right will take a negative sign. So F7 and F8, F9 and F10, these four forces will take a negative value, a negative sign. So yes, you can just calculate the area of the triangle or rectangle. Yes, these are area, but the area will take a negative sign to represent the direction of the force. So here, if you have a positive direction or a positive sign before the force, this means that the force is moving to the left. And if you have a negative sign, this means that the force is to the right. Then for the 10 forces, you will do the summation process and you will have a resultant force of 62.02 kilonewtons. This means that the resultant force is moving to the left because it has a positive sign. In the same manner, you will assume that for the moment, that any moment around the base in the anti-clockwise direction will take a positive value, and it causes overturning of the retaining wall. And any moment which has a clockwise direction will take a negative sign. So you will observe that for all forces from F1 to F6, the resulting moments will have a positive sign because they are anti-clockwise. So from F1 to F6, these moments have a positive sign because they are anti-clockwise. However, from F7 to F10, the moments are clockwise direction, so they will take a negative sign. Then you can do the summation process for your moments, and you will have a final resultant moment of 579.6 kilonewton meter. This moment has a positive sign, which means that it's anti-clockwise. At the very end, if you want to calculate the point of application of your resultant force, you can just say that the arm of this resultant force away from the base of the retaining wall, it's equal to sigma m over sigma f. The resultant moment over the resultant force will give you the arm 579.6 over 62.02. It's equal to 9.345 meter. This is the arm of your resultant force away from the base of the retaining wall.